Let's discuss data collection parameters for BioSonics 6 when you're collecting data for a calibration sphere. First up is our transmit pulse control, our ping rate. A speed anywhere from 10 to 15 pings per second works really well. Just remember, when you go slower, you have to hold the target in the beam longer to get a good number of echoes. Next is our transducer tab. Really, the only thing in here is to what mode you're going to be collecting your data in. If you have a split beam transducer, make sure it's in split beam mode. Also, just FYI, down here on axis calibration date, this is the date the last time your transducer was calibrated at our factory. We do recommend annual calibrations, so if it's been a couple of years and you haven't sent it in, please do. Next up is the transmit and receive tab. In here you're going to set your acoustic mode, make sure you're in active transmission. Transmit pulse duration, anywhere from 0.4 to 0.5 milliseconds is recommended. Our calibration data sheet has the theoretical value calculated using a 0.5 millisecond pulse, so anything outside of that may give you a slight difference in target strength. Start and end range, just make sure it's set to where you're going to be able to see the sphere. We do recommend having the calibration sphere anywhere from 5 to 10 meters below the transducer. Calibration correction, this would be the offset where you enter it, and you would calculate this in the next step when we analyze our calibration sphere acoustic data. And data collection threshold, we recommend using the full threshold minus 130 in most cases. Next is the sensors and mounting tab. The only thing you'll be entering in here is the depth of the face of the transducer below the surface in this box. Next is our environment tab. This is where you enter the temperature of the water in degrees Celsius. It's best to be within about a degree plus or minus of the actual value. This does influence the theoretical value that you'll be comparing your acoustic data to when you come up with a calibration offset. If you're in fresh water, just check this box. If you aren't in fresh water, uncheck this box and enter in the appropriate salinity. If you don't know what that is, 32 parts per thousand is a value you can use. Next is the bottom detection tab. While we don't have to have this enabled for collecting calibration data, it is useful for separating echoes from the bottom from all the other targets of interest when you're doing your analysis. So it's okay to go ahead and check this box and set your appropriate settings. Next is the echo detection tab. This is where you enable single echo detection. If you're going to analyze your calibration sphere data in BioSonics, you need to enable this. If you're going to analyze it outside using a third-party program, something like EchoView or Sonar 5, you do not need to have this checked. Let's go through the parameters real quick. Echo level minus 70 should be good for calibration sphere data. So should 0.75 to 2 times the pulse length for the maximum and minimum echo length for your echo recognition. Maximum standard deviation of split beam angles and maximum beam compensation. These influence how far from the center of the beam you're going to allow echoes to be recognized. Something like a 6 degree and minus 6 dB beam compensation would probably be a little more appropriate for this. Now that we've entered in our data collection parameters, we can go ahead and save this configuration to help ensure a consistent field calibration check data collection program. We apply a biodegradable no phosphorus soap to the face of the transducer, just a tiny bit to break up the surface tension so we don't get bubbles trapped on the surface when we put it into the water. Same goes for the CalSphere. So it is important to know the temperature of your water, as well as the salinity if that's a factor if you're not in fresh water. You don't have to be super accurate, but within a degree Celsius would really be nice. And as you can see, we have a nice little thermometer. It's evening out at 8.8 degrees Celsius. Yeah. Allow both the calibration sphere and the transducer to come to ambient water temperature before collecting data, whether you're doing it for fish, plants, bottom typing, or calibration. It might be hard to see, but we do like to have the transducer slightly tilted away from us, or toward just a slight tilt, so it's easier for us to get the calibration sphere underneath the center, so you're not trying to swing your line into where it's impossible to get because the transducer. It's important to make sure you get your calibration sphere in all the quadrants, so if you artificially can't get it to one side because of the way your transducer is placed, you might get a false indication that there's a problem. Okay, so we're logging data in BioSonics 6. We've got our bullseye display up, we've got the oscilloscope graph, and a regular echogram. So you can see we're dialing in, moving the sphere close to the center based on our XY phase information. Our amplitude you can see fairly well on the oscilloscope.
Try to get it in the center.
So David's just swinging the CalSphere through all of the axes as well as out of them, so we can see that, yeah, it actually left. We are collecting more data, moving the CalSphere around in this nice spiraling. Do you spiral in or out, Dave?
Both.
Whoa!
I spiral out, then I spiral back.
This is a multi-spiraling data collection, and when we look at the collected echoes, you will see how good they can look after you master the spiral and the diagonal. Our next step is to analyze and export single echo detections in BioSonics 6. First, let's go ahead and play back the file that we collected earlier. Alright, and we'll go ahead and click this echogram overview button so we see the entire echogram on one screen. I'm also going to turn on our single echo detections. They will be highlighted in red. If I click it one more time, they'll just be overlaid on the raw acoustic data. So you can see here is our calibration sphere trace. I'm going to go ahead and just draw a box around this. Left click, draw your box around there, and then right click in that box and choose Echo Summary Report. Okay, so this is displaying all of the single echoes that were detected during our calibration sphere data collection. This graph shows the X and the Y angle. In the bullseye graph, and as you can see as I scroll over this, the data below is scrolling to show the information for the echo that I have highlighted. So here again is we've got full coverage in the beam. Dave did a really good job. We've got detections in all 4 quadrants. We've got quite a few in the middle, quite a few around the edges. If we're happy with this, next we just choose export. And we want to check echo summary. And now you can just save it with whatever name you'd like as a CSV file. I've already done that, so it's just prompting me to say there. Okay, so that's done. That's our VisAC 6 part. I'll go ahead and close this graph, and let's move on to our next step, which will be in Excel. Our next step is to go ahead and analyze our single echo detections that we just exported from VisAC 6 using Excel or other spreadsheet software. So let's go ahead and open up that CSV file that we made. It's delimited. It is a CSV, so it's comma. I just hit finish. Boom. Okay. So now we've got all of our single echo detections that we extracted using VisAC 6, and just to count them, we've got right around 2,700. 3,000 echoes is a good number to strive for when collecting data for calibration sphere. You don't need much more than that, but much less than that, then your results may be more ambiguous. So let's go ahead and we'll just double click on all these files. There we go. Get our So the columns we're interested in right now are the X and the Y angle columns and the target strength column here. So first, let's go ahead and highlight our entire sheet, and we'll go over to filter, turn on the filter. And in both the X angle and Y angle, we're going to filter out single echo detections, and we're going to choose the between operator. So we want to go greater than minus 3 degrees, less than plus 3 degrees. Same with the Y. So now this is just showing us all of the single echoes that were between minus and plus 3 degrees of center in both X and Y angle. And if you look, our number of echoes, we still have almost all of our echoes, 2,700 or so. So now I'm just going to copy the target strength column, and I'm going to paste that into a new sheet. Okay, so now we have all of our target strengths for the single echoes with an X and Y angle between minus and plus 3 degrees of center. The next we're going to do is we're going to take the 95th percentile of this column, and we're going to use that value as our target strength offset number that we'll be comparing to theoretical. So let's go ahead and say equal percentile. Highlight my column and 0.95. Boom. Okay, so it comes up with the number minus 39.25 dB. Our final step is to compare the theoretical target strength value of our calibration sphere given the speed of sound in water and either fresh or seawater to the value that we calculated our 95th percentile in our spreadsheet step. So all we need to do is first identify our speed of sound. So if we go back to our VISAC 6, we'll go to Playback, View File Collection Settings, and then down in the Environment tab. So you can see we entered a temperature of 8.8 degrees Celsius. We are in fresh water, and if we look, our calculated speed of sound is 1441 meters per second. Okay, so now we'll go back to our sheet, and 1440, that's close. And we just go over to our freshwater column and we look, and it says minus 39.7. So that theoretically should be what the target strength of our calibration sphere would be. FYI, down at the bottom it says the accuracy of the computed target strength is plus or minus 0.2 dB. So there's a little bit margin of error in this calculated value to keep in mind. Now if we go back to our CSV sheet, we see that 39.25 round up to minus 39.3. Back to our sheet. Okay, so minus 39.7, minus 39.3, we have a 0.4 dB difference between theoretical and what we are 95th percentile. So we're within less than a half a dB of where it should be. That is pretty good. If you wanted to include that though as a calibration offset, you could do that either during a data collection in VISAC 6. Here, calibration correction, since we are 0.4 dB higher than theoretical, you would want to put a negative calibration correction in here. So negative 0.4 dB, if that's how you wanted to do it. You could also add this calibration correction offset, whatever you want to call it, in the analysis, either in something, a third-party program like EchoView or Sonar 5, or Visual Analyzer. So there you have it. Let's go over the steps we need to conduct a field calibration check of our DT-X Scientific Echosounder. First is to select VISAC 6 data collection parameters. Remember that you can save the configuration for later use. Don't forget to update your environmental parameters when you need to. Next is to deploy the DT-X, ensuring the transducer and calibration sphere are allowed to come to ambient water temperature before collecting data. And remember that applying a little bit of soap to the face of the transducer and the calibration sphere reduce the amount of trapped air bubbles. Next is to collect 2500 to 3500 pings total, with 500 to 700 per split beam quadrant, and another 500 to 700 within 1 degree of the center of the transducer. Next would be to export the detected echoes from VISAC 6 to a CSV file that you can look in Excel. When you have the spreadsheet open, go ahead and filter the detected echoes within plus or minus 3 degrees, both X and the Y directions, and then take the 95th percentile of the corresponding target strengths as your calibration offset value. Next step would be to look up the theoretical value on the CalSphere datasheet, remembering to look at the appropriate sound velocity and water type column, and then compare that value to the value that we determined in the previous step. If your calibration offset value is more than 2 dB different than theoretical, please contact BioSonics, and thank you for choosing BioSonics for your hydroacoustic needs.
Never could believe the things you do to me.